Hello, my name is Greg Armstrong, and welcome to the tutorial on ORAN fundamentals and synchronization overview. Before we talk about ORAN, let's first reintroduce ourselves to the radio access network. This slide is just summarizing the evolution of the radio access network since 2G. A lot of the details about the radio access network can be found in other tutorials. The key thing to highlight here is there was an operator-led alliance that was formed in 2018 that created what we call the Open Radio Access Network Alliance. And the idea behind this alliance was to try to open up some of the architectures of the radio access network to allow for more competition and faster deployments of the radio access network. If we look at synchronization, we can see that 5G is driving much tighter synchronization requirements. So we still see the known maximum time error of 3 microseconds, which was both 4G and 5G targets. But because of the disaggregation of some of the equipment being used for the radio access network, some of the tighter alignments needed between the clusters of radio units need to be within 130 nanoseconds peak to peak, or plus minus 65 nanoseconds from a common distribution unit. The ECPRE specification done by 3GPP has set a number of time error budgets for the user network interface. We will focus on the ECPRE timing accuracies of categories A, B, and C, because these are prominently the ones that are required for time synchronization. And they're also the most relevant to the Open RAN applications, which we'll get into later. The figure below is just illustrating some of the reference points and definitions that come from the ECPRE when we talk about front haul networks, which we'll talk about in the later slides when we get into ORAN. So what is ORAN? Well, as I mentioned earlier, this is an operator-led alliance that was initially formed in 2018. And what they wanted to try to achieve is the usage of standard interfaces and standard off-the-shelf components to basically deploy the radio access network. And the idea here is they would define all of the standard functional splits of the radio access network, allowing them to maximize common off-the-shelf hardware, silicon, and minimize the usage of proprietary hardware. This also would lead to standardization of open software and APIs to control and manage the Open RAN network. The drive for openness has many different reasons. Of course, the interfaces become standardized, which allows many different operators to interop with each other and the equipment they use to interop with each other. Operators can now mix and match different components for each of the different core pieces of the radio access network, such as the central units, the distribution units, and radio units. And components become more interoperable, which means the protocols were very clearly defined to allow this interoperability. So before we jump into synchronization for ORAN, let's talk a little bit about the architecture and functional splits. As I mentioned earlier, ORAN defines all of the functional splits and options that will be used by the Open RAN Alliance. The figure above is all the functional splits of a traditional radio access network, all the way from the RRC all the way down to the physical link or the RF component. The ORAN Alliance has defined many different ways to take these functional splits for different deployment scenarios, which we'll talk about in some later slides. Although the ORAN Alliance has come up with many different deployment examples, they primarily are focusing on two for initial deployments of ORAN. The first is a centralized radio access network. Here, the ODU and DU are typically co-located or fairly closely tied to each other through an edge site network. Typically, the connection between them is using a mid-haul interface. Between the DU and the radio units is what we call the front haul interface. And here you may have a front haul switch or MUX, or it may be a direct connection from the DU to each RU. And the RUs create what we know as a radio unit cluster between that distribution unit. The other deployment scenario is a split RAN, where they're actually splitting the CU from the ODU and RU combinations. Here, instead of a front haul switch or MUX, we're using a mid-haul switch and MUX to connect the CU to the DUs. The DUs and RUs effectively are co-located, and you can look at it as almost like a traditional baseband unit type deployment scenario. This slide is just trying to get into a little bit more details of some of the example functional implementations for the radio unit, distribution unit, and centralized unit. The key is I want to highlight is near the bottom of all the synchronization components that are going to be required, such as the I2T synchronous Ethernet, the IEEE 1588, and you can see that the common blocks are common between the radio unit and the distribution unit, and maybe even within the centralization unit as well. So now that we talked a little bit about the functional splits of ORAN and some of the deployment scenarios, let's look at how synchronization comes into play for ORAN. Because ORAN is focusing on the first two deployment scenarios, they are really only focusing for time synchronization between the distribution unit and the radio unit. The time and synchronization plane for ORAN, or the front haul interface, will use synchronous Ethernet, SSM messaging, and IEEE 1588 PTP packets to distribute timing from the DU to the RU, or between a centralized timing source to the DU and RU. The relative time error between the DU and RU has to be within the 3 microsecond specification. However, which we'll talk about later, in addition to that, a lot of the ORU clusters will have the 130 nanoseconds relationship back to its DU, which becomes important when we start looking at some of the timing requirements for each of these components. The current version of the ORAN specifications focuses on the transport of P2P and synchronous Ethernet directly to the radio unit, or what we call full-time support. Although usage of partial or assisted time support may be looked at later, it is not currently being focused on in today's ORAN discussions. As I mentioned earlier, because they're focusing on two key deployment scenarios, with that, they came up with 4 ORAN synchronization configurations or lower layer splits that they will focus on for C1, C2, C3, and C4. Configuration LLS-C1 or configuration 1 uses point-to-point and tightly couples the DU with the RU. The use cases for this can be for massive BMO radios, which require very tight baseband processing at the RU and DU, and they are basically focused with the split of what we call split 7.2, which was introduced earlier. A lot of times this will be used when there's a lot rural or less dense cellular networks and private networks are required, and if there's some mission critical network slices that need to be done as well. For time synchronization, the typical flow is going to be from some sort of time source like local GM to the distribution unit. But in this case, the synchronization to the radio units comes directly from the distribution unit. So the distribution unit is acting as the master for both synchronous Ethernet and PTP timing to the radio unit. This allows for a lot more synchronization resiliency for mission critical applications because you have a direct path of synchronization. And it's very similar to how 4G CPRE worked with the baseband units interface to the remote radio units. Configuration 2 is very similar to configuration 1, except that it allows for some switching within the front haul network. Now these switches are normally going to allow you to set up now radios in more of like a mesh configuration to allow for DU load balancing and maybe some bandwidth optimization. A lot of times these DUs may be even stacked within data centers, And there'll be some fail-safe redundant paths to allow the front haul network to use timing from any of the DUs within the network. So again, this would be used in like small cities, IIoTs, or other network slices that require this type of distribution configuration. For synchronization, the synchronization path is very similar to C1. The difference is there's now a topology that allows for switching of synchronization within the front haul network. So this is where it becomes important to understand some of the timing requirements between the radio unit and the distribution unit, especially if the radio unit clusters have to have the 130 nanoseconds of time error to the within each other towards that distribution unit. Configuration 3 looks at where instead of the distribution unit being the source of timing into the front haul network, the front haul network itself has a time source and is now providing that timing not only to the radio units, but also the distribution units themselves. So again, like the LLSC C2, the configuration allows the usage of switches, and again, allows you to do these mesh configurations and things like that. But now a lot of your fail-safe and redundant networks in the front haul for timing is coming from multiple primary reference time clocks that may be deployed within the front haul network itself. And the distribution units are no longer required to provide this timing into the network. In terms of timing and synchronization, again, the radio units really are not seeing any difference in terms of how they're getting their synchronization. The difference is mainly at the DU, where instead of the DU mastering the timing, it is now taking its timing from the front haul network. Finally, we have configuration LLSC4. LLSC4 basically eliminates the network synchronization component of the front haul network. It does this by effectively defining that both the DU and RU will have a connection to its own local time source. So again, these could be used for very mission critical applications where we don't want to have to rely on the network synchronization component to deliver synchronization. So again, a lot of times the sync flow is going directly from your local grandmaster or local primary reference time clock directly to the DU and RU. Sometimes, however, you still may want to use network timing as a backup. So again, you could use something like C3 as an overlay onto the C4 configuration to allow this backup option. Now that we talked about some of the configurations, let's look at some of the key equipments that make up the front haul network. We already talked about the ODU and ORU. So the ODU, when it's providing the clock into the front haul network for configuration 1 and 2, because it's providing the clock into the network, it must meet certain time accuracies as the primary clock into the front haul network, which are shown here at 1.4 and 1.3 microseconds. In addition to a time accuracy, the ODU is also responsible for providing a frequency accuracy onto the front haul network of 15 ppb for a Class A ODU or 5 ppb for a Class B. For the radio unit, it doesn't provide timing into the front haul network, so its time accuracy is not really relevant. However, it does have to provide a certain level of frequency error into the radio unit in order for the combined frequency component for the radio access network to be around 50 ppb. In addition, because the radio unit is recovering a clock off the network, it also has to provide some sort of maximum time error that's introduced onto the recovered clock. The ORAN has broken the ORU into two types of radio units. One they call a regular radio unit, in which it has to provide less than 80 nanoseconds of max time error, which is very closely related to like what we called Class B type clocks for the ITUT boundary clocks and time slave clocks. Or it needs to really beat less than 35 nanoseconds for its enhanced, which effectively is getting closer to like Class C for the ITUT telecom boundary clock and telecom time slave clock. Now, if configuration 4, where the radio unit may be connected directly to the time clock through a PRTC or whatever connection. Here, it has to be less than 30 nanoseconds of introduced time error onto the clock. Some other components that will make up the front haul network is the front haul multiplexer and the front haul bridge. The front haul bridge effectively is like any other bridging equipment that's used in networking, such as a network switch or a router that is basically switching packets and synchronization clocks throughout the network. A lot of times we would refer to ITU-T specifications to define these, either as a telecom boundary clock or a telecom time slave clock. And generally we would recommend trying to at least get something that's close to Class C in order to meet the tight cluster requirements of the 130 nanoseconds of all the radio units within a common cluster. You may also see a front haul gateway being introduced, and this is basically bridging traditional or existing networks onto the new 5G O-RAN networks. And again, a lot of times here, the front haul gateway may be acting as a distribution unit, so effectively it may be using much of the same characteristics and clock types as the ODU, for the timing accuracies and frequency accuracies. Or it may just be acting as its own kind of interworking function where it might be bridging the synchronization from one domain into the other. So maybe acting almost like the ODU, but it also could be acting as its own interworking function going from a backhaul network into the front haul network, or even the mid haul network into the front haul network. Well, I hope you found these slides useful and you've got a lot more information about O-RAN and specifically tied to synchronization. If you have any questions, feel free to reach out to me at greg.armstrong.uw@renesas.com, and I'd be more than happy to help you out. Thank you.